Okay, now I want to talk about other time marching methods. So probably you have heard this one. This is a very famous one, which I want to now talk about and give you some um, kind of details about its general form. Probably you have mostly heard four-stage type of it, but I'm gonna also introduce the two-stage of that, and that is Runge Kutta method. Uh, Let me start it here in a new page. So Runge Kutta methods. So the first point that I want to make here is that it is a multi-stage and one-step method. So these are all multi-stage one-step methods similar to the Euler one, right? The Euler was also multi-stage, but we only had one step. And after that, after this, I'm going to introduce a multi-step method, so you understand what is the difference. The difference relies on the time step that you are taking. So in all these one-step methods, we are only taking one step in time, right? So we go from Tn to Tn plus 1. And in multi-step methods, you are doing it for multiple steps. We will see that in a moment. So the second note that I want to make is that the general two-stage Runge Kutta method can be written as this. So U star is Un plus alpha 1 delta T f at n, at time n, which is a known function. And then the next stage is Un plus 1 is Un plus delta T times alpha 2 Fn, f at time n, plus alpha 3 F star. And F star is defined as F at U star, at here. What is F there? So you get U star here, you calculate F at that time, U star, using U star, and Tn plus alpha 1 delta T. So what you are going to do for you, so Fn is clear, right? You will calculate it based on Un and Fn, which you have it from the previous step here. But F star, what you are going to do, you first calculate U star here, and then in the function of f is a general function. It can be a linear function, it can be a nonlinear function. For example, it can be something like u squared plus, I don't know, 4u cosine like pi over u, something like anything, right? It can be anything. So what you are going to do for f star, first you will find U star from here, You have a delta t, you have like alpha 1, alpha 2, alpha 3. You set that based on the problem you want to seek. And then UN is the previous values of that, so you already have all of them. You calculate U star, and for F star, instead of UN, which you used before for calculating Fn, you are gonna use U star. So here you are gonna put U star, and then if for example you can also have t here, time here, for example sine t, something like this. And then instead of t, you're gonna put Tn plus alpha 1 delta t. Okay, so that is how you're gonna calculate, you will calculate U star, F star. Okay, so this is the second point for a general two-stage Runge Kutta method. And Taylor series, if you do a Taylor series, you will see, so Taylor series analysis shows that 1, consistency requirement requires that alpha 2 plus alpha 3 should be always 1. Okay, so this is a consistency requirement. And 2, second order accuracy requires, so this is, let me just show it. This is a general two-stage method. Alpha 1, alpha 2 plus alpha 3 should be 1. And this requires to alpha 2 be 1 minus 1 over 2 alpha 1, and alpha 3 to be uh, 1 over 2 alpha 1. Okay, so this is, if you want to have a second order accurate method, you have to set alpha 2 and alpha 3 based on alpha 1 like this. Okay, and you see that here also the alpha 2 plus alpha 3 equal to 1, which satisfy the consistency requirement. So this gives an interesting result, and that is, hence, corrected Euler method, Euler approximation is a two-stage Runge Kutta method with alpha 1 equals to what? So corrected Euler method was like this, right? As you see, alpha 2 and alpha 3 are both 1/2, and alpha 1, which is here, is 1, right? So with alpha 1 equal to 1. So as you see, corrected Euler approximation is just a subset of these Runge Kutta, general Runge Kutta methods. So corrected Euler is also a two-stage Runge Kutta method. And Runge Kutta methods are more general form of multi-steps, multi-stages, one-step, multi-stage, one-step methods, okay? So now I want to introduce the more common form of Runge Kutta method, and that is four-stage Runge Kutta method. So you see how it is and how it is defined, okay? And after that, we will talk about one-stage multi-step methods. We will talk a little bit about the whole idea of that. And then probably in the next lecture, we are going to introduce Adams' method, which is a multi-step one-stage method. Okay. So let me say the last point of Runge Kutta here. So for a stage, Runge Kutta method, which is the most popular fourth order method, is shown as this. So in the first stage, you do U star is UN plus delta T over 2 Fn. Okay, this is the first stage, simple forward Euler step. And then the next stage is what you're going to do double star is UN plus delta T over 2 times F star. And I will define what is F star. And then the next step is U triple star is UN plus delta T F double star. And finally, UN plus 1 is UN plus delta T over 6 Fn plus 2 F star plus 2 F double star plus F triple star. Okay, this is a four-stage method. And where F star is defined as F U star T N plus delta T over 2. F double star is defined as F at U star, U double star, T N plus delta T over 2, and F triple star is defined as F U triple star T N plus delta T. Okay, so these are the definitions of F stars that we used here. And so this is a four-stage Runge Kutta method, which is fourth order, very accurate, and is used a lot in most of the numerical methods that you might see. For example, MATLAB has its own function of Runge Kutta method, and you can use it, and other software also have similar time marching methods. Okay, so this is a general most popular fourth order Runge Kutta method, which is a four stage one step method. And by one step, I mean you just go from un to un plus 1. So you have only one step here. And now I want to say what is multi-step, like what is multi-step methods. So these were all one-step methods. These were multi-stages, but one step. And I want to now talk about one-stage and much-step methods. Okay. So the next topic is one stage, much step methods. So the idea here is to approximate du over dt and fut using values at tn plus 1 at different steps, tn plus 1, tn, tn minus 1, until tn minus p. Okay, so these are tn to tn minus p. uf, u, and f are known here, right? We know it from previous steps, and we only don't know u at tn plus 1 and f at tn plus 1. Okay, so these are the steps that we already know, and these are previous steps. Okay, and this if you use all these steps, it is this approach is called p plus 1 step methods, right? So if say p is 0, right? If p is 0, then you only are gonna use tn and possibly tn plus 1, and this is called one-step method, which was what we already saw. If p is 1, okay, if p is 1, then we are gonna use tn plus 1, tn, and tn minus 1. So this is gonna be two-step method, okay? Especially this tn and tn minus 1, where we are using two steps in the past to calculate the new value of u at tn plus 1. Okay, so this is the general idea of that. And now I want to talk about this implicit and explicit idea that we already talked in Euler method, and the same idea is also here in this one stage much step methods, and also talk about their accuracy and order. And in the next lecture we are going to show one example of this, which is Adams-Bashforth method. So when f is evaluated at tn plus 1, calculation is implicit, right? Because we don't know the value of f and u at tn plus 1, but we already have to use them in order to be able to get the value at get the new value of that. So we have to use matrix algebra to be able to solve for the new value of u at the new time step. Okay, this is the first note. And alternatively, when f is evaluated at is sorry, I have to say is not evaluated at t n plus 1, calculation is explicit. Okay. In general, explicit methods can be up to order delta t to 2 pi, depending on the order accurate. And this is for, in general, for one stage much step methods, because much step methods, and this is not for multi-stage methods. And implicit methods can be up to order delta t 2 pi plus 2 accurate. So this is the order of the approximations for much-step methods, one-stage much-steps or multi-step methods. Okay. Okay. So in the next lecture, I am going to show you one example of these one-stage much-step methods, and that is Adams' open or closed, that is implicit or explicit formula. So you understand how you should use these multi-step methods in your numerical schemes. And after that, we are going to combine both spatial discretization in space and in time together in a finite difference scheme, and see how you can solve a general partial differential equation using these things that we learned so far. Okay. So let me just have a brief review of what we learned today in this lecture. So first, we started with this variable weighting method, and we tried to find stability criteria for that. And we found, based on the definition of these variable weighting method, we found that this is actually going to be the lambda of that, and we use the criteria for stability criteria for these initial value problems, which is this one. And the right one just gave us a trivial condition, which is delta t is greater or equal to 0. And the left one gave us this criteria. And we found if theta is smaller than is greater than 1/2, this always holds. And if theta is smaller than 1/2, then in order for this variable weighted method to hold, we need this condition to be valid. Okay, so this is a conditional stability in this condition, and if theta is greater than 1/2, it's going to be always stable. And we said if theta is 1/2, which is kind of a Crank-Nicolson method, then we are going to have second order accuracy and unconditional stability, which is the best form of this variable weighted method. And then we started talking about Euler method in general. We showed the corrected Euler method, which is a two-stage, one-step method based on this. The first step predicts un plus 1 using forward Euler. And then the second step corrects that prediction. So it is also called predicted corrected method, okay? Then we talked about Runge Kutta methods, which are multi-stage one-step methods. These are general multi-stage one-step methods. So general two-stage Runge Kutta method is shown here. And then we showed with Taylor series can be shown that alpha 2 plus alpha 3 should be 1. And in order to get a second accuracy, this requirement should hold. And so the Euler approximation is actually a two-stage Runge Kutta method with alpha 1 equal to 1. Then I showed the famous four-stage Runge Kutta method, which is the most popular fourth order time marching method, which is this one here. And these are the definitions and how you, the coefficients that can be used to get this fourth order accuracy, which is a four-stage one-step method. And then we introduced the one-stage match-step methods. The idea is that we are going to use the older than previous steps, the solutions at previous steps, rather than having multi-steps in multi-stages in one step. We're going to use the solutions that we already know, for example, Tn minus 1, Tn minus P, in order to approximate the temporal evolution of the solutions. So when f is calculated at Tn plus 1, the calculation is called implicit. And when it is not, it is called explicit, which means we already know that Fn. And in general, explicit methods can be up to order delta t 2p plus 1 accurate, where p is the number of steps that you have. For example, if you have one step and one step and one stage, your method, let me see, if you have yes, if you have one step method, so one step p is going to be 0. So for p is 0, you are going to have delta t, order delta t for explicit method, and for implicit method, for one step methods and one stage method, one stage and one step method, your order of accuracy is going to be order delta t square. And so in general, it is delta t to power 2p plus 2, depending on the p and the number of steps that you have, okay? And p is just the number of steps that is shown here. And for example, this is a p plus 1 step method, okay? So this was a brief review of what we learned today. And as I said, next lecture, I'm going to introduce Adams method, which is a general form of one-stage match-step methods. Thank you very much, everyone.